For those of you that might be a little anxious about using technology to start doing numerical integration, let me give you a quick run through of how it's actually relatively straightforward to build numerical integration in Excel. This is one of those exercises that in the long run, people probably aren't going to use Excel to do numerical integration. However, being able to successfully get Excel to do numerical integration really shows that you understand the process and how all the pieces fit together. And that is what this is all about. So here on the screen, you see that we're about to take a crack at the integral from 0 to 5 of the function e to the negative sine of x dx. By now, hopefully, you would recognize that we have no hope of doing this integral by hand, and so we're going to do numerical integration to at least get an estimate of the value. And what are we actually calculating? Well, here I have Wolfram alpha plotting the function e to the negative sine of x on the interval from x equals 0 to x equals 5, and we are finding the area underneath that curve. So just doing it by hand with the fundamental theorem of calculus isn't going to work. And just to start with here, we will take a crack at a left and right hand rule approximation, as you're going to do in your own exercises. And so there what we want to do, remember, is to build an expression. And pardon me while I type a little bit. I'll probably snip this out so you don't have to sit through it. So for numerical integration, what we are going to assemble is this Riemann sum that's built and assembled for our function and our interval. So for the one that we are going to do, when we find the area under this curve, we're going to be integrating from 0 to 5 of that function, but we're going to do it in an approximate numerical fashion. So that means we need to chop the interval from x equals 0 to x equals 5 up into smaller chunks, smaller sub-intervals or partitions, and the number of partitions we make depends on how many calculations we want to have to do to assemble this numerical integration. Now here Excel is going to do all the work, so frankly I don't care how hard we make it, but just for ease of entry and intuitiveness, we'll keep it small. So let's say that we're going to go over here to this graph and we're going to chop the area under this region up into 6 standing rectangles. Well, you know what? Let's make it 5. If we chop the area under this region into 5 rectangles, each rectangle will have a width of 1, right? So let's do that. So what we're going to do is start building. Whoops, go back to the right screen. We're going to build a spreadsheet that's going to carry out this summation for us, where we're going to subdivide 0 to 5 into 5 intervals. We're going to pick a representative x-coordinate out of each of those intervals. When we use the left-hand rule, it's the left edge of the partition that's the representative point. When we use the right-hand rule, it's the right edge of the partitions that are the representative points. And then delta x would be the width of every partition or every rectangle. And here that's just going to start out being 1, but we'll build things so that we can change it. So now I'm going to open up Excel. In Blackboard, I've created a template Excel file for you to start with already. And so you're free to go grab that and just start adapting it to your own needs for the problems you're doing. I'm going to kind of assemble things from scratch, and then you can see how that template file or something that might look very much like it would arise. So the crucial ingredients in this problem start with, we're going to call them A, B, and N. Let's center this stuff. Let's make sure everything we do is centered so it's easy to see. There we go. So for this particular problem, we're integrating from 0 to 5, and we've decided we're going to chop that region under the curve into 5 pieces for the moment, but we might change that number later. And so that information can give us a resulting delta x. Delta x, the width of each partition, is by formula b minus a over n, or in Excel speak, it's this cell, B3, minus this cell, B2, over this cell, and as we already knew, our delta x is equal to 1. Now what do we need? Well, let's go back to that picture. For every rectangle that we make, we need to get a list of the endpoints, which are this time going to be 0, 1, 2, 3, 4, and 5. That'll be a pretty straightforward list. And we need to pick representative points from each of those intervals and the value of the function at those representative points. So let's label one column the x sub i's. Those are going to be the endpoints, and f of x sub I, that's going to be the value of the function at each of those endpoints. Now, I could type these in manually. Whoops, by going 0, 1, 2, 3, 4, 5. But that's a bad way to do it, because what if I decide I want to go back here and change n to 10 or 20 or 100? I don't want to have to keep reconstructing this column by hand every single time. So what I'm going to do is, in the first endpoint spot, I'm going to specify this value as my first endpoint, because it is. And then to make all the other endpoints, all I need to do is start at this endpoint and add a delta x to it. So the next endpoint would be equal to the previous endpoint plus this value. And you can't see my keyboard, but I'm hitting F4 when I've selected that cell, because that will then keep the referencing to that cell fixed. And then what I will do is just copy this down the line. And I'm going to stop here because I know that I only need to go from 0 to 5. Now, as the heights of my partitions, I will be using f of 0, f of 1, f of 2, and I'll collect different sets of these depending on whether I'm going through the right-hand rule or the left-hand rule. So I need to build our function here. Now remember, the function was e to the negative sine of x. Ugh. Well, in Excel, the exponential function can be called up with exp. And then I will have minus sine of x. Now my x coordinate is the number sitting in this cell, so I'm going to click that to get the reference, and I'm going to close out my parentheses. And let's see if that's consistent with the graph. At x equals 0, is this graph growing through y equals 1? Sure it is. Okay. And so now I'm going to copy this right down the line. And now I've gotten f of x for all of those endpoints. Now this table shows me that the values start at 1, they go down, then they go up. So a little dip and then a rise, and that is consistent. There's a little dip and a little rise. There we go. And so I have confidence that these are the right values. So for this image, I've done my partitioning into 5 sub-intervals. I've created the list of endpoints, 0, 1, 2, 3, 4, 5, which are the edges of those sub-intervals. And I've calculated f of x, whoops, don't do that, f of x here, f of x here, f of x here, etc., so that I can collect together heights of rectangles. Now, which heights am I going to collect? Well, it depends if I'm doing the left-hand rule or not. Remember that to build this numerical estimate of our integral, we need to make a summation of f of x times delta x. So we have our endpoints, we have our values of f of x. I'm just going to call delta x capital dx. So what I need to do is grab, for each one of these, grab f of x, so here equals that f value times delta x, which in this particular instance is back here. And again, you can't see my hand moving, but I'm going to select F4 to keep that referencing fixed. Copy that down. The numbers didn't change, right? Because we're multiplying by 1. Now, for the left-hand rule then, I'm going to go back here and I'm going to add up the f of x times delta x for every left-hand endpoint of those partitions. This one was a left edge, this one, this one, this one, and this one, but not the last one. This is the endpoint at the very right-hand side of everything. It is the right endpoint of the final partition. It's not one of the left-hand endpoints. So if I'm going to build my left-hand rule approximation to this integral, I'm going to sum, and Excel, that's equals. Equals always calls up the function you're about to operate with, sum. Sum says, hey, we're about to add stuff up. What are we about to add up? Well, f of x times delta x for 1, 2, 3, 4, 5 left-hand endpoints. Don't grab that last one. There we go. The right-hand rule estimate, we're going to go over here and add up all of the f of x times delta x's for the right edges. This one is not the right edge of any of the partitions. The rest of them are. So I'm going to go grab those, and there we have it. So the left-hand approximation to this integral we're looking at is about 4.8. The right-hand estimate is 6.4. Left hand is probably underestimating, right hand is overestimating. Now, we might decide, you know what, 5 partitions, that's no good. That's not going to be nearly enough to get a decent estimate for this integral. So what if I wanted to change the number of partitions to 10? Well, I don't have to reconstruct everything. All I have to do is go back here and change n from 5 to 10. Notice a whole lot of stuff has changed automatically. First of all, delta x has gone from 1 to 1/2. That's good. My endpoints are not 0, 1, 2, 3, 4 anymore. They're 0, 1/2, 1, 1.5, 2, 2.5. Now, because we have more endpoints, we need to extend our list all the way down. So let's go down to 3, 3.5. This is kind of a guess as to where to stop. There, did it. But these calculations are coming along for the ride when we copy those down as well. So this value right here is e to the negative sign of this value, and this is the f of x value to its left times delta x. And remember, delta x is now 0.5. So 0.71 is 1/2 of 1.42. That's good. And then to go make our left-hand rule work, well, I'm not just going to add up these endpoints anymore. I'm going to add up all of the left-hand endpoints. There will be 10 of them now. I'm going to omit the very last value because that's not a left-hand endpoint. And then for the right-hand endpoint, I used to be adding up these endpoints. Now I'm going to go to the very end of the list. And now we have left and right-hand approximations for this integral for 10 subintervals rather than just 5. So the actual value for this integral is probably somewhere between 5.2 and 6. Let's go over here. I'm going to pull up Maple, and I'm going to ask Maple to integrate that function on 0 to 5. And the answer is about 5.62, which is definitely in between these two values. Now, how is Wolfram Alpha getting this numerical estimate? Well, it's doing something very much like the left and right-hand rules. Conceptually, it's just a much more sophisticated process. These right here, these are the baby steps into numerical integration. What's going on over here in Wolfram Alpha is much more sophisticated, but you can't figure out what's going on behind the hood there if you don't already understand left and right-hand rules. So this is the easy way to build up one of these calculations in Excel. And during next week's topics, you'll see computer exercises which start doing a little bit more sophistication with these calculations. But for now, we will just leave it at this. Maybe as a final example, just real fast for those of you still sticking around, what if I wanted to get an estimate with 50? I'm gonna get this integral really, really good. I'm gonna do 50 partitions from 0 to 5. Well, all I have to do is take this and extend these calculations all the way down until I hit 50, until I have a list that shows me all 50 endpoints. There, let's see, how are we doing? Oh, I was one off, so let's bring this one down again. There we go. For our left-hand approximation, I've got to add up more endpoints. Oops, I overshot. So let's go back here. Let's pick everything but the very last value, which does not correspond to a left-hand endpoint. And then for the right-hand rule, let's go down and pick up that very last endpoint. And then we'll see how we're doing with 50. Wow, look at that. Now we've got it trapped in between 5.54 and 5.7. And again, remember, the Wolfram Alpha estimate is about 5.62. So with 50 partitions, we're closing in on it pretty well. Now, these more sophisticated techniques that we'll learn a little bit about in the next week can get us to this kind of accuracy with a very small number of partitions. Here it took 50 partitions. We can probably get to this close within maybe 10 or 12 with more sophisticated techniques, and that's what's going to come next.